Hello and welcome to the vodcast about states of matter for water. This is a diagram that is also known as the phase change diagram. If you have your notebook with you, please make sure you have this diagram ready to go. The X and Y axis, draw with a ruler X-axis along the long side of your journal paper, so turn that book sideways. The X-axis represents the energy in the form of heat that we add to these particles. And the arrow at the end shows that as you travel along the X-axis, the heat energy increases. On the Y-axis, we're measuring temperature. Temperature records how much energy those particles have. So you have increasing energy as you go up the y-axis. So down here at the lowest energy and the lowest temperature, what you see is the solid ice, and draw these little particles. These represent how close the particles are, and of course you know they're moving extremely slowly, but they never stop moving. The particles are held in a lattice work grid structure where they're attracted but repelled from each other, and that kind of locks them in so they can't go very far or very fast. And this makes sense probably that as you're adding heat energy, the temperature is also going up. So as we add more and more heat this way, the temperature of course is rising. But then we get to this one point right here, and we reach a place where there's just enough energy added in that now these particles can overcome that mutual attraction they have to each other, and now they don't have to be in that latticework structure. They break free of the latticework and they're floating around in a liquid. And as you can see, that line here, that energy is still going in, but the temperature is not going up. Now why would that be? We still have energy, but what we're doing is we're using that energy to break apart those particles instead of getting them to move faster. We have to overcome that attraction, and it takes that energy to do that. So we have the melting process, which takes more than a little bit of time. As you know, it's not an instant process. You saw this in the frying pan lab. There was a variation of how much ice was left and how much water was left until you finally get all of the ice melted. And at this point now, we have a liquid. So go ahead and draw your liquid. The liquid increases in temperature now as the energy is added to it. The particles are farther apart. They still have a slight attraction to each other, but they're not locked into that grid structure. They can glide and slide past each other. They have like a fluid motion, you could say. And then we get to a place that's higher up. As you add more energy, those particles are moving much, much faster now. And then we reach the point where they can break free of the surface. You have some boiling up. You see the bubbles of water vapor that is forming at the bottom of the beaker. And the ice particles are all gone. The liquid is boiling up, and you see those bubbles. Inside those bubbles are the vapors from the water changing to the gas form of water, the water vapor. And guess what? Here we have the flattening of the temperature again as we use that energy to, instead of make the particles move faster, it takes that energy to actually boil that water up. And after we boil, then we have the form of states of matter, the form of matter called gas. And you can see that the temperature continues to increase after that boiling once we get that matter into gas form. Now in your lab the other day, we only got to about this place where the water was boiling really vigorously, and we didn't measure any of the gases, but you saw evidence of gases because as they got closer to the glass of the beaker, those particles that you can see here very far apart, very fast moving, if they got close enough to that glass, the glass was cooler than the steam, and those particles became attracted back down to each other because they slowed down and they begin to get denser, closer packed together. This is called condensation. Now we're taking energy back away. Instead of going up the scale here, now we're taking energy back away, going back down the scale. So condensation, the opposite of boiling, is changing the gas back to liquid, and that temperature that happens is called the condensation point. As the material is a liquid, this liquid water, it loses more temperature as we take more energy away, and those particles slow down so far that they can no longer overcome their mutual attraction, and that's called freezing at the freezing point 0 degrees Celsius, and we go from the Freezing creates that solid again, and we're back down to the slowest particles and the least amount of energy. So quickly to review, you have the 0 degrees temperature at freezing and melting, depending on which way. Are you adding or are you taking away energy? And at 100 degrees Celsius, are you adding energy and boiling, or are you taking energy away and condensing? So please feel free to go back through this, review this. I would say the best way to review this is to close the book, try to draw it from memory, and then see where you went wrong, and then test yourself again. Thanks for listening.